All right, so we left off here, about ready to talk about resonance. But before I do that, does anybody have any questions from last time? As you went away and thought about the things we went over, is there anything you want to look at again or need clarification on, or make sense? Okay. So today we're talking about resonance. So now that you understand that sound has a size to it, that there is a physical space relationship between the sound that you hear and the places where those things exist, which is that if you understand how fast it travels and you understand what's happening, you realize that you can define it in terms of actual lengths and distances that you could measure with a tape measure. And that becomes important in a lot of ways, but one of the ways it becomes important is in the concept of resonance. And what resonance basically is if you have something, whether it be a physical space, like a room full of air, or some other physical medium that is able to vibrate, and you couple that physical thing with a sound that has a wavelength that is compatible with that physical space, or if that sound, in other words, if that sound fits in or on that physical piece of whatever, whether that's the piece of air in the room or the piece of string on a musical instrument or whatever, then that sound will kind of throw a party in or on that space. Think about it in terms of, like, here's an example of a string, okay? And what we're showing here is maybe somebody, like, twirling a jump rope or something like that, okay? Well, if you attach that rope to the other end of the wall and start shaking it, you could start making little patterns and waves out of it, right? And the ones you could make would depend on, how fast you moved it, okay? You could make it do different things. And that's resonance. So you find a speed at which you could shake it that suddenly it goes, oh, I could make that work and do a cool little trick, right? So that's called resonance. Now, in the case of like a string like this, the wavelength of that first frequency that will resonate on it, that wavelength is going to be twice as long as the string. And that's what's sort of attempting to be illustrated by this diagram. So the actual wall is here, and the string is attached to the wall here, and the person is hanging onto it over here, okay? And so what I'm showing you is what would happen is you would be shaking this, and it would be going up, down, up, down, up, down, okay? Up, down. And this would represent 1/2 of the wavelength of the actual frequency you're making, because if you're going up, then the other half of it, if the wall wasn't there, the other half would be doing that, right? It would be doing the... Is that sort of making sense? Okay. So the what we call the fundamental resonant frequency, the lowest frequency that you could make fit on that string, would have a wavelength that is twice as long as the string is. Okay? That is the point I'm trying to make. So, and it turns out that you could make other frequencies fit on that same length of string. So you have, this one here. Oops. So this one here is the one that was in the previous slide. Okay, so this is what's called the fundamental resonant frequency, where you're doing up, down, right? Well, the second frequency would be doing this, right? You could shake a little bit faster, and you'd get an up and a down fitting in at the same time, right? Or, okay. And you could shake it a little bit faster, and you could get something like this out of that same length of string. You could shake it a little bit faster, and you'd get something like this out of that same length of string. These are all different frequencies that you could make fit. Okay? These are called harmonics. The harmonics are not something that I'm going to need you to worry a whole lot about from some of the math I'm going to teach you. The main thing I want you to focus on is the fundamental resonant frequency, which is this one here. The fundamental resonant frequency is the one we're going to sort of predict and do math on, okay? The fundamental resonant frequency is the lowest frequency that can fit or resonate on that thing. This can also work not just in strings, but it can work on air. And usually where we care mostly is where it happens in the air. So let's think about like a pipe. Anybody ever like blown into a bottle and you get the sound to come out of it? Okay. That's kind of what we're talking about here, which that concept manifests itself in lots of different musical instruments, right? You blow air into or across something and it makes a sound, okay? Well, it turns out that if you were able to do that and the pipe was open at both ends, okay? So you see how it's kind of small, but you see it says open there and open there. So this pipe is open at both ends, and if you could get that pipe to resonate the fundamental frequency, then the wavelength of that frequency that resonates would be 2 times as long as the pipe. So if the pipe was 1 foot long, the frequency that would resonate in that pipe would have a wavelength that is 2 feet long. Okay? And then I'm just sort of showing you how that shakes down if we were to draw a little graph of a wave here, okay? So half of it fits in the pipe, and the other half of the wave goes the other way. So if it's a pipe open at both ends, then the fundamental frequency has a wavelength that is twice as long as the pipe. Here's where it gets interesting, though. If you cap one end of that pipe, so now one end is closed and the other is opened, and you try to resonate the air inside that pipe, that fundamental resonant frequency will now have a wavelength that is 4 times as long as the pipe. Or in other words, it becomes a lower frequency that resonates in that pipe. So this time, if the pipe is 1 foot long and it's closed at one end and you blow across it, then the frequency that you get out of it is going to have a wavelength that is 4 times as long as that pipe. Okay, before we get to the math, let me demonstrate how this works. I'm going to resonate this room. Are you ready? Let me actually get off of the right frequency. So I'm going to turn this on. This is just a little sine wave, okay? And I'm going to sweep this sine wave and I'm going to get to a certain frequency that's suddenly going to get loud. It's going to get really loud, okay? Because we get a little bit of it just coming out of the loudspeaker, right? But eventually the room is going to start resonating this frequency. Okay, you ready? Ooh, you hear that? Hear how it suddenly got louder? Quieter. A little bit louder, right? Okay, the room is resonating. Now what I want you to do, this is the interactive part, I want you to get up out of your seat. I want you to walk the room a little bit. And what you're going to find is there are spots where it will be loud and spots where it will be exceedingly quiet. And I would like you to find one of the spots where it's very quiet and then just stop there. Okay? Okay? Yeah.
About 20 hertz out, it was really screeching.
Yeah. Okay, so everybody find a spot where it's quiet and stand there. Okay, what frequency are we talking about here? 114 hertz. What is the wavelength of 114 hertz? The wavelength of 114 hertz. We learned how to do that math last week. Eric?
If we're doing math on a calculator, it'd be close to 10.
Yeah, if we just say it's 1,000 divided by 100, let's say it's 100-ish hertz, a little bit more. So we would say 100 divided by, or 1,000 divided by 100 would be 10. So a little bit less than 10 feet. How far apart are Reese and Connor standing?
Yeah, from 10 feet.
I'd give it like 8 feet.
So close.
9-ish feet, somewhere around 10 feet, a little bit less. Look how close Kat and Jasmine are standing. Look how Kat and Connor are standing. Look how Thania and Reese are standing. Everyone is spaced out approximately 10 feet. Okay? You get it?
Is that recording me having like the dumbest facial
Okay.
expression?
All right.
It's just me.
Now you can sit down. So,
I know.
okay, so what just happened? Well, so I resonated the room. So what was happening, the reason it got louder is it didn't get louder everywhere. Like Connor made a point saying where he's happened to be sitting, when I said it got louder, it actually got really quiet for him because he was sitting in what is called the node. Okay? But for me, it was loud. So, yeah, Jasmine?
What's
The
the node?
node.
Oh, the node. Oh.
Yep. So the node is the spot in the wave where no movement is happening, and the antinode is the spot in the wave where the most movement is happening. Okay? So it was no longer just the loudspeaker making the sound. The room was now contributing to this, right? That sound we found a way for that sound to fit in the room such that it resonated, okay? And it just locked right in between some two walls in this room. It go, whoop, okay, I fit. And then it just kind of starts regenerating upon itself, okay? And so you have these spots where it gets really loud and these spots where it's really quiet because you are actually sitting in a wave that is stuck, okay? It's called a standing wave. I've just proven that it can happen in a real room. Now, if it can happen in this room, it could happen in any room, including a theater. So, for reasons that we will learn in a few weeks, we humans are not very sensitive to low frequencies. We don't hear low frequencies as well as we hear high frequencies, and there are good reasons for that. And so that's part of the reason why we're always trying to get more bass, right? Because we're not very good at hearing bass. And so we're always trying to get more and more low frequency because we're really bad at hearing that. But the other thing is low frequencies have a tendency to do what just happened in this room. Low frequencies tend to create standing waves and resonate in a room. And if that's happening and half of your audience is sitting in a node and the other half of the audience is sitting in an antinode, it doesn't really matter how big of a subwoofer you have or how loud you turn it up. It's not going to change the fact that half the people are hearing it really loud and half the people are hearing it really quiet. Now, keep in mind, we're only talking about pure tones, sine waves right now, and in real life we deal with much more complex sounds than this one. So there's a lot more to it than what we're experiencing right now. But in principle, I want you to understand that that's what happens when resonance happens. So a sound fits on or in whatever the thing is. And that causes a couple of things to happen. One thing that happens is it gets louder. Okay? Another thing that happens is if you are inside of the thing that is resonating, like the room, or if you could somehow stick your head inside the pipe, the big pipe organ or something, or whatever, you will hear the wave doing its thing in the air. You will hear the spots where you have the compression, and you will feel the spots where you have the refraction, and you will feel the spots where it is not moving at all. Okay? Kind of interesting, yeah? Okay. So maybe you understand now why it might be useful to be able to predict some of this. So let's do a couple little pieces of math here. So here's one that we can do in our head. What is the lowest frequency that will resonate in a 1 foot long tube or pipe that is closed at one end? Okay, well, if it's closed at one end, we know that the wavelength of this frequency that we have to find out, we know that the wavelength will be how much longer than that pipe? 4 times. So that's going to be 1 foot times 4, which is 4 feet. So it's a 4-foot wavelength, right? Okay, I know wavelength. I want frequency. So that's going to be the speed of sound divided by wavelength, which will be 1,000 feet per second divided by 4, which is what? 250 hertz. So the lowest frequency that will resonate in a 1 foot long tube that is closed at one end is 250 hertz. You're not going to get anything lower than that to resonate in that pipe. Okay? Everybody okay? Everybody?
Let's say 4 feet, or let's say 4
So the wavelength, we figured out the wavelength is 4 feet. But yeah, this is, I'm trying to draw the symbol for wavelength. Sorry, I'm not doing a very good job at it. It's this.
It's the lambda.
Yeah.
What's it called?
It's called lambda.
Lambda?
LAMBDA.
Okay.
Yeah. It's like it's Greek. It's a symbol that is used for wavelength in math. Okay, so the people that do math tell me. I don't actually know. But the people who make decisions about those things have told me that that's the symbol that you use, and I have no reason to not trust them. Okay. But it is just a variable. We could, I guess, use any symbol we wanted as long as we all agreed that that meant wavelength. Okay, next one, another one in our head. What is the wavelength on a string of the fundamental resonant frequency for a 2-foot piano string, let's say? So you got a string on your piano that's 2 feet long. Some frequency will resonate out of that, okay? What is the wavelength for whatever that string is, whatever that frequency is? So we don't have to, I'm not asking for the frequency, I'm asking for the wavelength, okay? So Jesse says 4 feet. So a piano string, pianos have a string that is tied at both ends, right? So it's static at both ends, which means we're talking about the wavelength would be twice as long as that, right? So yes, it would be 4 feet. The reason that question is worded kind of weird is because on a piano string like that, there is tension and density also play into what frequency ends up resonating on that, and we're not going to get into that. So figuring out the actual frequency that would come out of that involves some variables that I don't need you to understand in order to make my point. Okay? All right, another one. Fundamental resonant frequency of a closed 10-foot long hallway. So what I'm talking about is if we had like a hallway in a room, and I'm doing like a plan view for this thing. Okay? It's a hallway like this. Closed means the doors are closed at each end of the hallway. In fact, all the doors, even if there are doors on the long end, they're all closed. It's all closed, enclosed space. Okay? And there is 10 feet end to end on this hallway. All right. Well, turns out that Well, this is not unlike a pipe, okay? And it turns out that a pipe closed at both ends does the same thing as a pipe that is open at both ends, okay? So it's only when one end is closed and the other is open that it does something different, okay? But if it's closed at both ends, it's just like being open at both ends. And if it's open at both ends, how long is the wavelength of the lowest resonant frequency? Twice as long, right? So if it's 10 feet long we're talking about, then the wavelength is going to be 20 feet, right? And if wavelength is 20 feet, then we just take the speed of sound divided by 20, and we get what?
50 hertz.
Yeah. 50 hertz. There you go. All right. Here's an interesting little tidbit of information. How many of you have had the experience where you pull up next to a car that is stopped at a stoplight and you hear freakishly loud bass coming out of that vehicle? Yes? We've all had that. And how many of you have had the opposite experience where you sit in a car and have a really tough time getting the bass to be loud enough inside that car? Right? Have you had that experience? Okay. This is why. How many cars have a space inside of them between two fixed windows or walls or whatever that is 10 feet long or more? Right? 10 feet-ish. Not very many cars. Most cars are smaller than that on the inside, right? Which means that low frequency is going to have a hard time resonating inside of there. Because to do what that frequency has to do, it needs a bigger space of air than that. And where does it find that space of air? Outside the car. Okay? So it's, cars are not entirely airtight, and so you've got that big subwoofer inside the car trying to make that sound, and it's trying to figure out how to do what it has to do, and it figures out how to do what it has to do by using the air that's outside the car. Okay? Which is kind of interesting. Now, what you might find out is if you crack the windows of your car, the bass gets louder. Why? Because you've created a bit more air for that subwoofer to work with. Okay? That make sense?
Yes.
Try it sometime. It's kind of cool.
What if you're surrounded by a space that's like closed and there's like walls are like 1 foot away from your car?
Yeah, I mean, it's going to be hard for you to get consistent, loud sound out of low frequencies, right? Frequencies that are lower than 500 hertz. It's not that you won't be able to hear them. It's just going to be hard for you to make them very loud. Okay? All right. Using a calculator. All right. What frequency will a 2.5-foot organ pipe produce? I don't know a whole lot about organs and how they work. I mean, I know the gist of it. But for purposes of us doing interesting math, let's assume that this particular organ pipe behaves as though it's a pipe that is open at one end and closed at another end. I don't know if that's exactly how they work, but I think we're going to assume that for now. Okay? So organ pipe means one end is closed. So if I ever ask you a question about an organ pipe, that's how I think they work. I don't know if I'm right on that, but for purposes of us having conversations, we're going to assume that that's how organs work. Okay? So if it's closed at one end, what would be the wavelength of the frequency that comes out of that pipe?
4 times that?
It'll be 4 times that. So it'll be 2.5 times 4. And what does that equal? You should probably do that in your head, right? 10 feet? That shouldn't be too tough. But if you need a calculator, go ahead and do that. Okay, so the 10 feet, the 10 feet is the wavelength. Okay, so now to figure out the frequency, that's going to be 1,130 feet per second divided by 10 feet. And what is that?
113.
Probably do this in your head too, but maybe a calculator. 113 hertz. Okay?
Why did we include 1,130?
Just because I used that, I said use a calculator. So when I say use a calculator, we want to be slightly more specific about the speed of sound. Okay? But if you just want to figure out something in your head, you can approximate things. I call it earballing. You got to earball it, okay? So if you're earballing it, 1,000 feet per second is close enough to get you an answer that you can take some action on, okay? It may not be exactly right, but it's close enough that you'll know what you need to do. Okay, next one. What frequency will that same pipe produce if I shorten it by 6 inches? Okay, well, how long was it before? 2.5 feet. So now it would be 2 feet, right? So now it's 2 feet, which means the wavelength is going to be 4 times that, which would be 8 feet. And now we would do 1,130 feet per second divided by 8 feet. And what is that? 141 point what? 25. I need one more person to get that. I got 2. Seth got that? Okay.
Yeah.
141.25 hertz. At least 3 people got that answer, so it's probably right. Okay?
Yeah, you're going just a little bit fast.
I'm trying to get to comb filtering. So.
I know.
You got it? Everybody caught up? All right. Here's the fun one. Let me go back. What are the 3 fundamental resonant frequencies of a room that is 16 foot by 6 foot by 8 foot? Okay, let me attempt to illustrate. So I'm going to attempt to kind of like do a little orthographic view here of what I'm talking about. Okay. Okay, if I draw that, does everyone understand what that means? Okay. So this is a cube, right? Now, the parts of the walls that we can't see on the inside, I could represent by the dotted lines, okay? And they might be. Does that make sense? Does everyone understand what I'm drawing here? Does anyone not understand what I'm drawing? Okay. So if I measure from this wall to this wall, we would call that 16 feet, okay? And if I measured from this wall to that wall, I could call that 8 feet or 6 feet. I mean, it doesn't really matter. And then I could measure from this wall to this wall, and that would be my 6 feet. So this is what I mean when I say a room 16 by 6 by 8. Okay, there are 3 pairs of walls here in this room. Okay, one pair is 16 feet apart, one pair is 8 feet apart, and another pair is 6 feet apart. Everybody with me so far?
Not many people are going to stand up in that room.
No, I mean we're in theory world here. Okay. Okay, so this is basically, there will be 3 answers here because there will be a frequency that fits between those 16-foot spaced walls. There will be a frequency that fits between those 8-foot spaced walls, and a frequency that fits between those 6-foot spaced walls. Okay, so let's just solve them one at a time. So for the 16-foot wall, that will have a wavelength that is 32 feet, because twice as long, right? So 16 times 2 is 32 feet. So that's the wavelength, and then to find the frequency, we would do 1,130 divided by 32. What's that? I need 2 more people to get 35.31 hertz. Yes, yes, yes. Okay, does everyone see how we got there? All right, next one is the 6-foot which if we multiply that by 2, we get 12, right? So that's a 12-foot wavelength. So now we do 1,130 divided by 12. What's that?
94.17.
94.17. Anybody else get that? Yes. Okay. Hertz. Very good. And now, what about this 8-foot? Well, we multiply that by 2, and that will be 16, right? 16 feet. So 1,130 divided by 16. 70.63 hertz is what Reese got. Anybody else get that? Yeah. Seth got that? Connor got that? Okay. Must be right. There you go. 3 fundamental resonant frequencies of that room. Now remember, those are not the only 3 frequencies that will resonate in that room. Those are just the 3 lowest ones.
So if we had a problem similar to this, but it said like there was a window on the 6-foot walls, then we would calculate that times 4, 6 times 4?
Yeah.
Okay.
Yep.
Making sure.
Okay.
Thank you.
I'm not going to ask you a question like that, but yes, yeah, you're making connections, which is good. Anybody else got any questions? Okay, so that covers resonance, and that should give you the ability to answer a few more of the questions on that quiz.
Yes.
Okay.
You understand?
All right. There is another property of sound that we have not talked about yet. So we have talked about how sound has a speed. We have talked about how sound has a frequency. And we have talked about how sound has a wavelength. There are 2 other properties of sound that I want us to talk about. One is amplitude, and another is phase. So here I have a graph, or rather 4 graphs here. And this first one is whatever it is. Okay? Doesn't matter what it is, it's just a thing, right? It's just a wave. And the one right next to it, this one, what is different about it? Yeah, they're taller, right? Other than that, it is the same frequency. It is the same wavelength, right? It's not bigger. In other words, it's not any wider of a wave. But yeah, the peaks are taller, and the troughs are deeper. This is called amplitude. So that second wave has a greater amplitude. Now, amplitude in sound is typically what creates loudness. So higher amplitude is louder to our ears. Lower amplitude is quieter to our ears, usually. Okay? Everybody understand that concept? Anybody got questions about that? Okay. Well, now let's look at the bottom 2. This one is the reference now, and then look at the one next to it. This is the same frequency, it is the same wavelength, and it is the same amplitude. So something else is different. And the thing that is different is the phase. And what phase means is we know that the sound goes in this pattern: compression, rarefaction, and back to 0. So what phase of that cycle is it in? Are we in the peak compression phase? Are we in the peak rarefaction phase? Are we at the beginning phase of that cycle? Are we halfway through?
At what point of the wave are you talking about?
So this would be the peak compression. This would be the peak rarefaction. This would be the beginning phase. This would be the end phase. This would be the middle phase, right? And we could be all kinds of phases in between those places, right? You understand what I'm saying when I say phase? Anybody need clarification on that? So this thing starts wherever it starts. And it does a compression, then a rarefaction, and then goes back to where it started. So that takes time and space, as we've learned. So some of the simple, we could define that process in phases. So think about it in terms of an evil plan for world domination. Okay, phase 1 of my plan. Create a crazy conspiracy theory. Phase 2 of my plan. Get a bunch of people to believe it. Phase 3 of my plan. Get those people really riled up about it, right? Phase 4 of my plan. Get them to take over the world, right? Okay, the phases of my plan. Okay, in this case, my plan is to make a sound. And phase 1 is start from somewhere. Phase 2 is compress some air together. Phase 2 is stretch some air apart. And phase 3 is go back to the beginning again. And phase 4 is repeat that forever. Okay? So in this case, we have the first phase is start from somewhere. Second phase is peak compression. Then we go back to the middle. That's another phase. Next phase would be peak rarefaction. Next phase would be starting back over. And we repeat. Okay? Well, we need, so there's 1, 2, 3, 4, 5 different phases that we can define just using some abstract concept, right? But what if we want to understand other phases of this process? There are more phases. There's, in fact, quite a lot. What do we call this phase? Right? What do we call that phase? What do we call this phase? See what I'm getting at? All the spaces in between have a phase. Okay, well, if you think about it, this is a circle. This is another way of drawing a circle. So if I draw a circle, I go here and I go all the way around. So I start back, I end up where I started. That's how you draw a circle. You start somewhere and you keep drawing until you end up back where you started. Okay? Circle. Well, this wave is another way of drawing a circle. So I start somewhere, I go up, I go down, and I go back, and I'm back where I started. It's a circle. And we can define a circle in terms of degrees. Okay? So in this circle, I could say 0 degrees, 90 degrees, 180 degrees, 270 degrees, / 360 degrees. Right? So this would be 45 degrees. You see what I'm getting at? Yeah. Okay, so if this is a circle, and if the wave here is a circle, it's just a different kind of circle, then we could talk about this in terms. So this would be 0 degrees. This would be 90 degrees. This would be 180 degrees. This would be 270 degrees. This would be 360 degrees.
You know, those questions at the end of the test make so much more sense now.
Yes. This would be 45 degrees. See what I'm getting at? Yeah. Okay, so now that you understand that, what is different about this wave? It is starting at a different phase, isn't it? What phase is it starting at? 270 degrees.
Thank you.
It is starting at 270 degrees. So that second wave is 270 degrees out of phase with the first wave. Okay? You see where I'm going here? Okay.
I gotta figure out how to draw that later. I'm just gonna put a star there.
Now, why does that matter?
Can I guess why it matters? Like,
Sure.
If you have like two sounds coming out that are supposed to be the same and they're on different phases.
Yeah.
Like that could, coming out of the system, could that mess it up? Or
It
is
could. It absolutely could.
Okay.
So here's an interesting thing. We have learned about two different properties of sound in this one slide. One is amplitude, the other is phase. We can hear amplitude, right? I just said greater amplitude tends to result in us perceiving louder sound. Lower amplitude tends to result in us perceiving quieter sound. Here's the interesting thing about phase, though. We can't hear phase. So even though we can change phase and we can have a sound that is starting at a different phase, we can't hear with our ears that that sound started at 270 degrees. We can't hear that because we don't hear until it starts completing cycles. So where it began that cycle doesn't so much matter to our ear-brain system, because our ear-brain system doesn't really start perceiving anything at all until it has completed cycles. It has to like push that eardrum and pull on that eardrum a few times before our brain goes, oh, I hear a sound. Okay, so the phase is not something we can hear. That's important. We cannot hear phase. Remember that. No matter what anyone tells you, we can't hear phase.
Can you feel it though?
No.
Okay. I was wondering if it, no. I was just like, there are some things you can't hear, but you can like feel them. And
We can measure it,
yeah.
right? There are tools we have that can measure it, but we cannot hear it.
You can hear the effects of it when things are out of phase.
You can't. You cannot hear phase. Here's what you can hear, though, and this is maybe what Jesse is thinking about, is what we can hear is the result of two sounds combining together at different phases. So if we took the first wave and the second wave, generated them independently, and then combined them either in the air or inside of, your mixing console or whatever, you combine those two sounds together, we can hear the result of that. We can hear the result of those two sounds running into each other. Those two sounds separately sound the same to us. You play one, listen to it, stop it. Play the other one, listen to it, and stop it. They will sound exactly the same. You play them at the same time in such a way that causes them to run into each other, and that will create a result that we can hear. And I will prove it. Are you ready?
You're like, I do color.
I'm gonna equal 3.
Oh. Okay. I'm going to turn this down. I'm going to take this up to a little bit higher frequency so we don't have to worry about standing wave so much. Okay, so I'll take it to 250 hertz. You ready? So I can manipulate the phase of this wave. Let me see if I can slow this down at all. There we go. So I can change the phase. Can anyone hear anything changing? Okay. See, you can't hear it. Now, lest you think I'm playing a trick on you, let me create the same wave, which is 250 down here. Same sound, right? Now I'm going to put this one 80 degrees out of phase. Okay? So here's the first one. This is 250 hertz starting at, at zero phase. Here it is, 80 degrees out of phase. We cannot hear the difference, can we? Okay. Watch what happens when I play them both at the same time. I will now turn on the 80 degrees out of phase. Okay, what changed? Yeah, the amplitude changed. So now that we know that when you combine them together out of phase, it messes with the amplitude. Let's look and see what kind of amplitude messing around we can end up with. Well, if I take it to 0 phase, the result becomes twice as loud, or the amplitude goes twice as high. If I go to 180 degrees, it should cancel out. Let me restart them just because they get them synced back up again. There we go. Now I have no amplitude as a result. Why? Because they are in direct opposition to each other. One of these, I'm playing both of these sounds out of the same loudspeaker. And one of the sounds is trying to push the driver that direction, and the other sound is trying to pull the driver that direction. Well, the driver cannot both be pushed and pulled at the same time. Well, it can, but it just won't move. Right? It cannot both push the air and pull the air at the exact same moment in time. And therefore, the air just stands still. And so does the loudspeaker driver. Okay? So that's kind of interesting, right? Now, if I take it all the way to 360 degrees, I get the same thing as 0 degrees. It's twice as loud. Because remember, 360 degrees takes us all the way back to 0 where we started. So even though we are one full cycle out of phase, on a sine wave like this,
Can you interchange 360 and 0 degrees?
on sine waves, yes.
Okay.
Okay?
On different waves? On sine waves, yes. But on different
Cat's like,
waves.
there's more.
I like
So-
that it was specifically sine waves.
Yes. We will get to non-sine waves in a moment.
Okay.
Okay, let me show you a couple of other interesting things.
Yeah, I'll just let you have it.
Okay, so starting at 0, we know it gets louder. As I shift the phase, what's happening? The combined amplitude is getting quieter, isn't it? But watch this. When I get to 120 degrees, 120 degrees is when they combine with no change in amplitude. Right? If I turn one off now, the result is the same amplitude. Turn it back on, it settles back to the same amplitude. Right? So 120 degrees out of phase, they combine with no amplitude change is the result.
Why?
Because they are interacting both destructively and constructively just enough to result in no difference. Okay? So anything less than 120 degrees, and it will be louder to some extent. Maybe twice as loud if it's 0, right? But somewhere between 0 and 120, it will be louder as a result. But past 120, that's when it starts getting quieter as a result. You get to 180, and you've effectively canceled it out. Interesting little factoid. I take it up to 240, and that's the same thing as 120,
So with 360, yeah. Yeah.
right?
Okay.
So 240 is also no change in amplitude. Okay? Now, the take-home message here is that while we cannot hear phase, we can hear the results of two identical sounds, and that's the important part. They have to be the same. Two identical sounds combining out of phase. Right? We can hear that. We can hear the results of that. And the results of that tend to involve changes in amplitude. Okay? Everybody with me so far? All right. Let me make one more point here. And that point is there is another term that you will hear thrown around called polarity. So if I write polarity, I wonder what I mean. by that word? Well, polarity, let me go back here, reset that. There we go. Oh, I can't reset that. Okay, polarity. When you think about the way a loudspeaker works, for example, if you've ever seen a loudspeaker driver on the back, it has two little terminals, right? One of them is labeled positive, one of them is labeled negative. Okay? This is how alternating current, electrical signals of alternating current work. It's positive, negative, positive, negative, positive, negative. This is how magnets work. Magnets have poles, right? And that's what a loudspeaker. A loudspeaker is a big magnet. Okay? You put a positive pulse on that magnet, and it will push the coil forward. You put a negative pulse on that magnet, it will pull the coil back. Okay? Phase happens, changes of phase are very closely connected to time. Because in this scenario, where this second wave starts 270 degrees out of phase, there is a difference in time between that peak refraction of this wave and the peak refraction of this wave. They will happen at a different time. Do you understand why? Because sound travels 1,130 feet per second. Okay? And so we start here, and it will take a certain amount of time for us to get to there. And therefore, the difference here and here, there is time between when we get to those different phases of the wave. Right? It takes time to get there. And so one of the ways to create a difference in phase between two sounds is to manipulate time. And in sound, we can manipulate time. Did you know that? Sound designers are the closest thing to time travelers that we have in theater, because we actually can manipulate time. Usually we have the ability to delay things. So we can put a sound coming up, say, play a sound out of a loudspeaker, but do it sometime in the future. I'm going to create the event now, but I don't want it to actually exist until the future. So you're going to basically send that sound into the future. Okay? Yes?
Does that relate to, like in a theater, when you have, let's say, arrays and then front fills, and the angle at which they're hanging are going to hit the audience at one time, and the front fills are going to hit at another? Do you set the delay so they both hit at the same time?
Not necessarily.
But that's kind of like the gist.
Yeah, you don't necessarily want them hitting at the same time, but we have the ability to do that. So we can say, I want to make this sound now, but I'm going to send it into the future so that we don't actually hear it until we get to that point in the future. Okay? So we can move it into the future. We can't move it into the past. We don't have that ability. But we can move it into the future. And if we move it into the future, then when we hear it, it will be out of phase by a certain amount compared to the version of that sound that we do not send into the future. Right? So if we make that sound twice, and one of the sounds we let happen right now, and the other sound we send into the future, when we arrive in the future, when both those sounds are playing, they will be out of phase with one another.
Which will affect the amplitude, right?
Yeah.
Okay. I'm just making sure I'm
Which will
following
affect
here.
the amplitude. Okay? So phase is very closely connected to time. Generally speaking, phase is time for us in sound. Okay? Phase and time are so closely connected we can almost talk about them interchangeably. And oftentimes we do in our analysis systems. Okay? We actually use our ability to measure phase as a way of measuring time. It's one of the ways we can measure when something happened is by measuring its phase. Okay? You'll learn more about that when you take sound system engineering with me. But phase is very closely connected to time. Okay, now I want to go back to polarity. Polarity is just a difference between the positive pulse and the negative pulse. So think about that loudspeaker that has the positive terminal and the negative terminal. And you're hooking these wires up to it from a power amplifier, right? And one of those wires is the positive wire, and one of those wires is the negative wire. Well, what would happen if you flipped those wires around? And you put the positive wire on the negative terminal, and you put the negative wire on the positive terminal. What would happen? Yeah. So now that loudspeaker would operate backwards. It wouldn't blow up. It wouldn't get hurt. Nothing would happen. It would just be backwards now. So the sounds that are supposed to push out would now pull back. And the sounds that are supposed to pull back would now push out. That effectively inverts the wave. And it would be this, right? See that? I have inverted the polarity. But I have not sent that sound into the future, right? I have merely inverted the polarity. I have just crossed the wires. But I have not sent it into the future. And therefore, I did not change the phase.
Right.
But here's the interesting thing.
Oh, is this how you do this, the side, middle, side thingy?
Yes. So.
Sorry, I feel like I stole your thunder there.
No, I'm not.
Okay.
You're just like, you're like a year ahead of me right now. But you're okay. You're all right. So, so I inverted the polarity. Well, what would happen if I did send this sound into the future such that I caused a 180-degree phase shift? Well, it would look like this, wouldn't it? So I did two different things to this sine wave. One of the sine waves, I inverted the polarity, and the other sine wave I sent into the future, 180 degrees into the future. And I got the same result. But I did not do the same thing. Now, why is this important? Because we have the ability to do both. We have the ability to manipulate the polarity, and we have the ability to manipulate the phase. We can do both. But don't confuse those things, because they are not the same thing. They have the same result for sine waves. When you manipulate the phase and you manipulate the polarity, you can get the same result for a sine wave, right? Here's where this gets very, very confusing. So going back to our little demo here. So I now have my two waves. They are both in the same phase, 0 degrees, right? I am not going to send one into the future. I am merely going to manipulate the polarity on the second one. I'm going to invert the polarity. You ready? I inverted the polarity. And what happened? It canceled out, just like it did when I shifted the phase by 180 degrees. Okay? So I get a cancellation just like I did before. So everybody with me so far? It's a different, I did two different things, but I got the same result. Yes? Okay. Very good.
And the two different things was inverting the wave and
I both inverted the polarity, that was one thing I did, and I shifted the phase. Right? I did both things, but I got the same result. And I got the same result because I was working with sine waves. And now you're thinking, well, why is he making such a big deal about qualifying everything he's saying right now with sine waves? Well, because we don't always work with sine waves. Okay, we don't always, in fact, we rarely work with sine waves. Okay, so this is just a slide that sort of demonstrates those results we were getting with the little, the little software tool, right? So there's some situations, 180 degrees relative phase is cancellation, 0 degrees relative phase is a full reinforcement, it goes higher. 90 degrees relative phase, it's a little bit higher amplitude. 120 degrees relative phase, it's the same amplitude. Okay, you see that? All right. Now we get to the point. How are we doing on time? We're good. Here is the point. Now, we actually never, well, not never, but hardly ever, do we actually deal with sine waves. There are only two times we deal with sine waves. One is when we get feedback. Feedback is a sine wave, okay? And we tend to avoid that at all cost, right? So we don't want that to happen. So if we've done our job right, we will never hear that sine wave, right? You got a question? No, okay. Okay. The only other time that we deal with a sine, well, there's two other times we deal with a sine wave. One of the other times is sometimes we use a sine wave to test our system, right? So sometimes we use a sine wave to make sure that sound's going through it. And sine waves sound like square waves when you clip them. And so that's one way we use to kind of figure out if we've actually clipped or distorted something is by running a sine wave through it, and allows us to hear distortion really easily. So we use sine waves sometimes to test our sound system. And we use sine waves sometimes in synthesizers to actually build sounds, right? But other than that, other than those few very specific situations, every other sound we work with are not sine waves. They are actually what we would call complex sounds that have multiple frequencies happening all at the same time. My voice, for example, right now has multiple frequencies happening. I am not speaking to you in sine waves. I am speaking to you through my vocal cords, which are creating many, many frequencies altogether, many harmonics together, and that's what makes me sound like me, as opposed to what makes Lee sound like Lee, right? Or Jasmine sound like Jasmine, is our respective voices have different combinations of different frequencies that go together at certain amplitudes and everything to make us sound like us, okay? And that's great. And so almost every sound we ever work with has lots of frequencies in it. Now, in a complex sound that has lots of frequencies in it, if we make a copy of a complex sound and we send it into the future and combine it together, back again, that we have offset it in time, right? It's a difference in time. Now that difference in time for some frequencies, there are some frequencies that difference of time would result in some 360-degree phase relationship. And those frequencies would get louder. And then there are other frequencies where that amount of time would result in a 180-degree phase relationship. And those frequencies would go away. And then there are other frequencies that might have a 120-degree phase relationship, and they would stay the same amplitude. And there are other frequencies that would be maybe 140 degrees, and they would be a little bit quieter. And there are some frequencies that maybe would be 90 degrees, and they would be a little bit louder, right? So in a complex sound, you would have many frequencies, And when you combine it with a copy of it, with a clone of itself that has been delayed in time, and then sum them together, some frequencies get louder, some get quieter. And it turns out it's a very predictable pattern. And I've graphed it over here on the right. Okay? So if you graph that, this I delayed two identical sounds by 1 millisecond. So they are 1 millisecond apart. And when they are 1 millisecond apart, this is what happens. This frequency goes away, this frequency goes away, this goes away, this goes away, this goes away, this goes away, so on and so forth. These frequencies get louder. Louder, 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 louder. That frequency stays the same, that stays the same, that stays the same, that stays the same. This is called comb filtering. Because when you graph it, it kind of looks like a comb, like a hair comb, okay? Comb filtering is the worst thing that happens to sound people when you're trying to make good sound. You will spend the rest of your life chasing comb filtering if you decide to do sound the rest of your life. Because there are about a gajillion ways, approximately, to generate comb filtering. But they are all the result of two identical sounds combining with each other slightly out of time. Yes? Comb filtering is the result of combining two complex sounds out of time. And that result is that some frequencies get canceled out and some frequencies get louder.
Like when two actors sing towards each other. And
That is one of the bajillion ways that you can make it happen.
that's what it sounds like, though. It's like,
I'm going to let you hear what it sounds like.
oh, okay, good. I was trying to find a auditory example.
All right, are you ready to hear what this sounds like? So I'm going to create pink noise. And pink noise is all the frequencies all at the same time. Okay? Pink noise is all the sounds at the same time, all the frequencies at the same time. Okay? So I can't demonstrate comb filtering with a sine wave because comb filtering, it's a full spectrum phenomenon. Okay? So I'm going to create all the frequencies all at the same time. You ready? There. There are all the frequencies at the same time. That's what it sounds like. That's what pink noise sounds like. Now, I am going to make a copy of this pink noise, and then I'm going to delay it, and then mix them together. So there's one delay, there's a different delay, different delay, different delay, different delay. Okay? That's what comb filtering sounds like. Now you can see it being graphed here. You've got the cancellations and the reinforcements, right? Hopefully you can all hear that. Okay? Now, that's what it sounds like. This is not always a bad thing. I think it's probably usually a bad thing, but it's not always a bad thing. Sometimes we do comb filtering on purpose because it sounds interesting. Musicians do it all the time with a synthesizer. It's called flanging.
That's what it is.
Yeah.
'Cause it sounds like when
Flanging is comb filtering. Okay, it's just comb filtering that's moving around.
Phasing is comb filtering. Flanging isn't flanging. I might be thinking of chorus, but isn't that a slight variation in pitch
No.
rather than time?
Flanging, the term flanging comes from the old reel-to-reel tape deck days. And there was a thing called the flange.
Right.
And if you stuck your finger on the flange, you would torque the tape just a little bit. And if you had the same sound on both tracks of that tape, that same sound would run across the head at 2 different times.
You know, I think I remember you explaining this. I think we've had this exact
Yeah.
conversation before last year.
And no, like a reel-to-reel tape deck,
Oh.
right? So you put your finger on the flange and you mess with it, and you can torque that tape back and forth, and it will create a offset of time between when the 2 sounds on the 2 tracks on the tape run across the head, and therefore when they mix them together inside your mixing console, they create a comb filter. Now, if you like wiggle the flange, you can create that, what we now know as flanging, which is, right? Right? And that's messing with the flange. Okay, so flanging is comb filtering, all right? So comb filtering is not always bad. Sometimes we like it. Sometimes it's cool. But a lot of times it's cool when you do it on purpose, but it's not cool when you do it by accident, right? So that's what it sounds like. Now, what you just heard is what I call comb filtering on the wire. And comb filtering on the wire is what happens when you mix the sound inside of a piece of equipment. So you combine the 2 sounds together electrically or digitally or something, right? And then send them out. So that's what I'm doing. I'm combining them inside of the computer, such that what comes out of the loudspeaker is already comb filtered. And therefore, no matter where you sit or where you are or who you are, you will hear the comb filter. Okay? Let me show you another type of comb filtering. Did you know that you can comb filter in the air? I'm going to comb filter the air. Are you ready? I'm going to comb filter the air. And how will I comb filter the air? Well, I will take the 2 copies of Pink Noise, and I will play one of them out of that loudspeaker, and I will play the other one out of that loudspeaker. But I'm going to delay that one in time. So I'm going to delay that one a little bit. Okay? And so they're going to come out into the air, and they're going to hit each other in the air. Okay? And then they will comb filter. Now, you ready? All right. I'm going to do this in milliseconds. Okay, and maybe you're thinking, well, gee, Jason, that was really anticlimactic, right? So here's 0. There's 1. Well, get up and move and tell me if you hear it. My what?
Oh, did you just do an adjustment to it?
Yeah, I just turned it up. You hear it? Okay, so what's happening? Depending on where you stand, that time relationship is different. So the sound is coming out of that one 1 millisecond later. But if you are closer to this one, then you're hearing this one sooner than you hear that one, right? And so as you move around, because the sound takes time to travel through the air to your ears, okay? So depending on where you stand, you are changing that time relationship.
Is there a term for the point with 2 speakers out of time like that? I just feel like that.
Well, they all, well, I mean, they combine everywhere. You ready? I'm going to blow your mind now. I'm going to remove the delay. So I'm going to make them come out of both speakers at the same time. Now walk around the room. Wait a minute, Jason, it's still doing it. I thought you said you didn't delay it. Is that what you're thinking? Okay, so I said I removed the delay. They're coming out of both speakers at the same time. Why is it still comb filtering? Yeah, because when you move, you are a different distance away from each of them, and therefore you hear them at a different time. Okay? It is possible for you to find a spot where they both hit you at exactly the same time. It would take you a while, and in that spot, it would sound like louder pink noise. But that spot is going to be really hard to find because, generally speaking, no matter where you stand, they are going to hit you at slightly different times. Okay? All right. Everybody with me so far? Yes. You got it? Yes. Okay. So I have demonstrated both what cone filter, well, you now know what cone filtering sounds like, right? And I've told you there's a bajillion ways to make that happen, and I've shown you a couple of ways. One way is to make two sounds in your computer and then mix them together slightly out of time and then play them through a speaker, and you can hear it. And then you hear it no matter where you sit. I call that cone filtering on the wire. There's lots of ways to do that. And I've also shown you that you could make the same sound come out of two different speakers, and you can delay one of them, and that will cause a cone filter. And a cone filter is in the air. But then I showed you how I could not even delay them at all and just play the same sound out of two loudspeakers, and it still cone filters. Okay. So what does that mean then? Why do we care about that? Why do we care about that last part? That I can play the same sound out of two loudspeakers, and it will cone filter in the air if you are sitting in different places in the room. Yeah, because we do that all the time. That's literally what we do every single day of our entire lives as sound people. We play the same sound out of more than one speaker in a room and have lots of people sitting in different places in the room. All right? So it's like, I just told you that the thing you do all the time is the thing that creates the thing that you hate the most, which is that sound. Because you're all going, every time I cone filter, you're like, oh, that sounds terrible. All right? And I'm telling you that you do that all the time. You make that all the time. Which is one of the reasons why I tell you never play the same sound out of two loudspeakers at the same time. Have I ever told you that? I've told you that a million times, I think. Never do that, and yet you do it all the time. Here's one of the reasons why I tell you not to do that. Because when you do that, it does this, okay? So don't do that. Or if you do that, be very careful about how you do it. Because if you do it haphazardly, this is what happens. Okay? So cone filter on the wire, cone filter in the air. You now know what it sounds like. Here is, okay, before I tell you the next point, let me play another version of cone filtering. Okay? That's with pink noise. Pink noise is all the frequencies that are equal amplitude per octave. Now, you don't know this yet, because I haven't taught this to you yet, but I will teach this more to you in detail in a few weeks. But did you know that we don't hear every frequency the same way? We are not sensitive to every frequency the same way. Some frequencies sound louder to us than other frequencies sound, even though they are the actual same amplitude. I mean, I said earlier, we're not very sensitive to low frequencies, right? We don't hear those very well. We hear high frequencies really well. Okay? So pink noise sounds to us like all the frequencies are the same level. But if you actually looked at pink noise, you would see that they are not actually the same level. In fact, you can see here that they are not the same level, because I have graphed the pink noise in amplitude. And you can see that they are not the same level. But they sound the same level to us. Okay? So pink noise is all the frequencies not at the same level, but sounds like the same level. Okay? That hardly ever happens. We don't ever really use pink noise. Okay? We just use it to test sound systems. Real complex sounds that we work with every day, they don't have all the frequencies at the exact same level. They sound something more like this. Okay? But guess what? They can cone filter too. this isn't always a bad thing. Right? People get paid all the money in the world all the time to like do this. Oh, that sounds great. Flip that flange, right? All right, that's what it really sounds like, okay? But I'm comb filtering on the wire. Watch this. I'm going to flip it to the air now. So now I've got two copies of it, one playing out of this loudspeaker, one playing out of that one. I'm going to delay one of them. You ready? How many of you are hearing anything really, really noticeable?
Not really, but like slightly.
Yeah.
If you pay very close attention, you can kind of sort of hear something, right? But you have to really concentrate to hear it. Okay. Here's the good news about comb filtering. You have never in your life heard a sound that wasn't comb filtered.
Problem solved. Perfect.
And that is where we will end for today. We will pick this up next time, and I will explain what I just said. Okay? You have never in your life heard a sound that was not comb filtered.
Is not comb filtered?
Yes.
But I thought
You know this.
What's that?
I thought comb filtering was bad.
I said it's not always bad. I said it's usually bad.
Okay.